Hello, my name is Eric Newman. I'm an applications engineer in Keysight's PathWave software organization. I'm back today to show you how we can use Sys-Parameter models in ADS and show you how we can run more sophisticated system simulations using our fast circuit envelope simulation capability. In the last video, we showed how we could take a custom MMIC Sys-Parameter file into ADS using a data access component. The model included frequency-dependent information regarding the gain, reverse isolation, noise figure, and output linearity of the amplifier. We were able to model that and then run it in a system simulation using a verification test bench, in this case a 5G VTB. Today, we will add a PA to follow the driver amplifier from analog devices. We'll use the HMC 1132 PM5E. We applied a similar methodology to import the analog device's PA data into ADS. We exported Sys-Parameter data from SystemVue, and we used a few modifications to prepare it to be saved as an MDIF file format with an MDIF extension. We use a data access component in ADS to pull the data from the MDIF and interpolate data for the desired simulation frequency. We were then able to use variable equations to load the parameters into an RF amplifier model and run our frequency-dependent simulations. Today we'll start off simulating the HMC 1132 PA with a stronger input power of 0 dBm this time using a 5G filter bank multi-carrier verification test bench. In addition to a single data access component to extract the noise figure gain and linearity of the device, we are using a second data access component to extract the S-parameters which are available for the power amplifier, allowing for vector-accurate simulation of the input and the output impedances, along with the RF behavior. Users are encouraged to explore the provided workspace. Within there are several cells showing the methodology. Cell 1 shows a single static simulation at a fixed frequency and uses the MDIF file format to pull in the amplifier gain, noise figure, IP3, P1 dB. And we made an assumption that the saturated output power in this case is 2 dB above the P1 dB, as we did not have the PSAT data available for this part. We then showed how we can add a second data access controller and run a frequency sweep, allowing us to verify the power amplifier's large signal and small signal performance versus frequency. We also verified versus power with a similar setup, allowing us to study the compression effects and third order intercept behavior versus signal power. Now that the power amplifier's large signal and small signal RF behavior has been verified, we can now run the power amplifier in the same verification test bench that we used to test the driver amplifier and run it at a different power level and look at the EVM performance, peak to average ratio, ACPR, and spectrum. What may be more interesting is the cascade of the driver amp with the power amplifier. Here we are cascading the Custom MMIC CMD 243 driver amplifier with the analog device's HMC 1132 power amplifier. Rather than having multiple DACs for each model, cluttering up the schematic, in this case we're using hierarchy. So we can push in and we'll see the same kind of data access component and variable definition and amplifier models as we used before in the test bench, but now we are using them within a hierarchy. So we can push into the PA as well and see the dual DACs being used in this case. Again, we have an envelope simulation controller that was created by the verification test bench. In this case, we're enabling fast envelope simulation to allow for faster simulations. We have different levels we can include: memoryless, small signal with memory, and large signal with memory. For reasonable simulation speed, I'm going to go with level 3 using normal modeling accuracy. As the simulation proceeds, we can see in the simulation log that it is creating and saving a FCE, a fast circuit envelope model file. We can use this later as a behavioral model in our SystemVue tool. Simulation has completed in a little over 30 seconds, and we can again review our waveform statistics, look at our spectrum at the output of the power amplifier. See our EVM is about 32 dB now, which is acceptable. Our peak to average ratio is back up to what we had anticipated it to be, as long as we're not clipping the waveform excessively. We could run this at other power levels and study the ACPR and EVM behavior. Recall when we ran the simulation, we had the fast circuit envelope level 3 selected. By having fast circuit envelope enabled, we were able to write a file during the simulation with the same cell name. Fast circuit envelope also helps speed up the simulations in ADS, but it also provides another capability. It allows us to pass the models between the advanced design system and our SystemVue tool. I'll briefly open and modify a SystemVue example that we ship with the tool. It is found within the VTB libraries and is actually the same test bench we are using in ADS to simulate with our behavioral models. I'll go ahead and delete the SystemVue engine link from the workspace schematic, and I'll add a fast circuit envelope instance in its place. Double-click on the model, and I'll browse to the simulation we just ran and use the cascaded fast circuit envelope model. I now see that pins have been instantiated onto the model. I can set the parameters to same frequency power levels as I was using on the ADS side, and I can run the simulation or run the analysis here. And when the simulation finishes, I should hopefully see the same kind of spectrum I noticed in the ADS data display. And we can report back the same specs, EVM, gain, power. We can see about 32.2 dB EVM here. Same result calculated in the ADS environment. So this allows circuit designers, system designers to interact across the environments. You could imagine a system designer might want to add IF to RF frequency conversion stages, possibly some digital signal processing, all enabled within the SystemVue environment, while the circuit designer might go back and reconsider some of these behavioral models and replace them with their own transistor level designs and generate an FCE model to pass back to the systems engineer. I hope you find this video enlightening. Please feel free to reach me at my Keysight email address, or if you need additional support, please reach out to our tech support team. Thank you for your time.